Okay, welcome to Lecture 9 for ECE 203. In this lecture, we're going to focus on sampling. Okay, so for the most part for this course, except in lab, we've really discussed what are called continuous time signals or analog signals. And those signals are just functions of real valued variables, usually t, to indicate time. And so t can take on any value, right? Any real number. As an example, right, a signal we've spent a lot of time with is just x of t equals cosine 2 pi ft. Okay, and so that's defined for values of t that are, for example, 0.2 or square root of 2 for any real number. But as we know from doing the labs, to analyze and to process and synthesize signals using computers, the signals actually have to be represented just as sequences of numbers, which can be stored and then processed using software or algorithms. Okay, so again, there's this kind of disparity. We've spent a lot of time in class looking at signals of the form x of t, right? Continuous time signals where t is real valued, and in lab, when we're actually doing things in practice with signals, we've used signals that are just simply lists of numbers or vectors in MATLAB. So as an example of this, just to get us thinking about things that we're familiar with, one example would be digital audio, okay, or CD audio, compact disc audio. So this is a little dated at this point, right? This goes back to the 90s, and the idea here on a CD, the audio was actually sampled at 44.1 kilohertz. That means there's 44,100 samples per second of audio. So the audio is a continuous time signal, right? And then that's sampled at some sampling rate. And the sampling rate for CD audio is 44,100 samples per second. And there's about 16 bits for each sample. There's 16 bits that represent one sample of the audio. And of course there's two channels. There's a left and a right channel for stereo audio. So if you just multiply these things together, you'd see that a 3-minute song should take about 200 megabits, which is about 25 megabytes. Okay, so it's a fair amount of storage. If you use something like MP3 instead, you can see the songs get a lot smaller, and that's using compression. Compression is not something we're going to talk about yet, but we'll talk about compression towards the end of the course. Okay, so another example is just a digital image, right? And so a digital image, we have each pixel corresponds to some sampled continuous time value of the light intensity at some location. Okay, and so here think of for example, an 8 megapixel camera. That's what's in my phone, and that means there's 8 million pixels, 8 million samples of this this continuous space of intensities of light. Okay, so let's take a slightly more mathematical view of this, and let's first talk about analog to digital conversion, and that's the process of converting a continuous time signal to a discrete or a digital signal. Okay, and sometimes we'll just call that sampling. So the basic idea behind this is we have some continuous time waveform that's underlying what's going on, and let's say that's x of t. Okay, and that's defined by this green line, whatever the green line in this plot is. And then we're taking samples of this green line at different values of t. Okay? And what determines the location at which we take the samples is just given by the sampling period. So to be specific, what's written in this equation here, we have x, now we're using brackets, and n is x of n, and the brackets indicate that the values of n are just the integers. Okay, and so it's only for n equals, say, minus 3, minus 2, minus 1, 0, 1, 2, and so on. But what defines where these sample locations are is this value of t sub s. Okay, so t sub s right there, that's the sampling period. So every t t sub s seconds, we take a sample of the continuous time signal. So that's the basic idea behind analog to digital conversion. Relatively simple, and we can, if we have an expression for a continuous time waveform, we have x of t, we can just plug into this formula here and get x of n. Okay? So again, x of n is the discrete time signal, and it's just a list of numbers, and we can take that list of numbers and store it and process it on a computer. And once more, the key parameters here are the sampling period, t sub s, and that just defines, again, here this distance between the sampling points. Okay, and then secondly, f sub s, which is the sampling frequency or the sampling rate, and the units of f sub s. Sometimes it's just said in hertz, but we'll try and say samples per second to be very explicit. So f sub s is the number of samples per second, and that just equals to 1 over the sampling period. All right, so let's take a kind of a high-level view here of something that we might want to do. Let's just say we take a continuous time signal and we want to convert it to a discrete time signal or a digital signal, and then we want to convert it back to a continuous time signal. So we need two things to do that. The first thing here is an analog to digital converter. Okay, so A to D converter. And what happens here is there's an input. The input is the continuous time signal, and then there's a second input, which is the sampling period, and the output is a discrete time signal. Okay, so it's a system. An A to D is a system that takes a continuous time signal in and then samples it at some sampling rate. All right, it's just a block diagram here. So how do we get back to continuous time now that we have this discrete time signal x of n? Well, the way we would do that then is using a digital to analog converter. Right? So just think of this as another system now that takes as input x of n, which is a discrete time signal, or just a list of numbers, and again it has a sampling period, and then it reconstructs a continuous time signal from the discrete time signal. So when you're looking at this, you might say, all right, the A to D converter, the analog to digital converter, it's pretty straightforward. You have x of t, a t sub s, and then you get this discrete time signal. It's just a list of numbers. There's not a lot of different variants on how this could happen, right? So when we come down to a digital to analog converter, there's a big question that we're kind of glossing over, and that's now when we have this discrete time signal, some sampling period t sub s, and we want to get back to y sub t. What we haven't defined is what happens in between the sampling periods. How do we connect the dots? How do we interpolate between these sampling points? And there's various ways to do that, but before we look at that, I just kind of want to point out that these, A to D converters and D to A converters are not just block diagrams, but these are actually, real devices that if you're working as an electrical engineer doing hardware things, you'll become, depending on the position you have, be very intimately involved in maybe selecting some of these, deciding which ones to use for a particular product. So just as an example of A to D converters and D to A converters, I just kind of grabbed a few screenshots from a website. So these are examples for converting electrical signals to digital signals. Okay, so a voltage on a wire to a digital signal. And this first one up top, this is pretty amazing. This kind of blows my mind when I think about it. But this company Fujitsu makes a 56 gigasample per second 8-bit analog to digital converter. Okay, so what is? Let's remind people, what is 56 gigasamples per second? That is 56 billion samples per second. So I'll just write SPS. Okay, it's a lot of samples per second. Right? I think if that were to fill up the memory of your iPhone, it would take about 2 seconds to fill up something like that for a 16 gigabyte iPhone. Right? So this actually A to D converter is used in what's called coherent optical communication. So very high speed communications. It's used for links that kind of underpin the internet, okay, for optical communications. All right, and then kind of down in this lower right corner, I went to a website. It's called Analog Devices is the name of the company, and they make D to A converters, so digital to analog converters, and of course A to D converters also. And so there's a couple things I want you guys to notice, and that if you just go on their website, you can really see, you know, there's a lot of different specs. Each one of these things is a different part, okay? But the kind of the key things are, let's see here, the sampling rate. So it's written as the maximum sampling rate, and you can see, you know, the first one is 48 kilohertz, so 48 kilosamples per second. The second one's 192 kilosamples per second. And again, these are D to A converters. So this is the rate at which they're able to reconstruct. They're able to recreate this in analog signal. It's the rate at which the samples are output from the device with continuous time waveform. And then kind of the second thing that's important is this resolution in bits, right? And the resolution, that just means the number of bits that are used to represent the output signal. Okay, so that one way to think of that is the more bits, the more precisely you can represent a particular number. Okay, sometimes it's called effective number of bits for these D to A converters and A to D converters. But really, these are the kind of two key features of A to Ds and D to As. So the first one being the sampling rate, and the second one being the number of bits, which is the resolution or the precision at which you're able to recreate a particular value when it's either sampled or output from the D to A. Okay, and when either one of these goes up, the cost of the device goes up. So depending on, you know, down here, you could just go to this website, Analog Devices. You can see what the current price for these things are. But they're anywhere from, you know, 10 cents for a slow device, a slow D to A with a small number of bits, to hundreds of dollars for very specialized D to A's and A to D's. Okay. All right, so the question that was kind of at hand before we looked at a few of those actual devices, it was how do we connect the dots? So it was pretty straightforward to do analog to digital conversion. There weren't a lot of kind of different ways we could do it. It was really just one way. You give a sampling rate and then you just sample the signal. But how do we reconstruct the signal, right? So that, again, this is digital to analog conversion. How do we draw the lines in between these sampling points? And there's that mathematically there's many different options, right? Maybe you could do something, really strange, right? You could draw, I don't know, you could say in between each point there's a sine wave, right? That would be pretty ridiculous, but you could do it. And in reality, there's much more obvious options. One is what's called linear interpolation, okay? And linear interpolation is just when I draw a straight line in between each point, okay? So I draw a straight line from one point to the next point. That's called linear interpolation, right? Make a line between the points. I could also do stepwise, or what's sometimes called zero order hold. And that's just where I make a constant. I hold the value at the sampling point. I just hold the value constant until the next sample. And then I set a new value, right? And then hold that constant. And that's kind of drawn. I can draw it again up here in black, but it's like we hold it straight and then we take the next value, and then each time we get to a different sampling point, we hold its value until the next sample point. And so what you end up with is a kind of a staircase. All right, but it's pretty obvious to see now that both of these ways of connecting the dots, they should have smaller and smaller error, right, as t sub s gets tiny, okay, or as my sampling period gets small, meaning my sampling rate goes up, then my ability to somehow reconstruct the signal should get better, regardless of what method I'm using. Even if I'm doing linear interpolation, the stepwise, this constant, or more complicated things that we'll actually see later in the course. Okay, so that's just kind of an intuitive, maybe somewhat obvious statement, but we're kind of faced with a few questions when we're looking at reconstructing a signal, okay, and how all these things play together. And the first one is, well, it's pretty obvious that when we slow down the sampling, that we're not able to reconstruct particular waveform as well. So the question is, how fast do we actually need to sample, and how small do we need to make that sampling period, so that we can at least hope to somehow accurately reconstruct the original signal X. Again, the smaller TS's, smaller the sampling period, right? That means higher sampling rate. It means more samples, more storage on the computer, and then more cost. Remember the A to D's, the price went up when the sampling rate went up. Okay? But we have better reconstruction on the plus side. So again, if we make the sampling period larger, then the opposite happens. And you have fewer samples to store, okay, which is good. You need less memory. There's less cost. You can use cheaper A to D's, but the reconstruction is worse. All right. And so there's a couple more. You could come up with a long list of questions, but maybe a second one is, how well do these different methods of interpolation work? So linear interpolation, the stepwise interpolation, how well do they actually represent the original signal? And then the last question we'll ask is, how is that the spectrum now of, say, we take a signal X of t, it has a particular spectrum, and then we sample it using an A to D converter and reconstruct it using a D to A converter, then what is the spectrum of the reconstructed signal? And we can actually answer all of these questions just by studying various sinusoids. Okay, that seems like a good starting point, right? We've shown that we can represent any periodic waveform as a sum of sinusoids, right? So to start and to kind of get a good mathematical understanding for sampling sinusoids, let's just look at a single sinusoid. In particular, let's just look at this, the equation we've seen so many times, right? X of t equals a cosine 2 pi f naught t plus phi, right? And when we're sampling, the key thing is going to be the frequency, and that describes, again, intuitively how fast the sinusoid is changing. If the sinusoid is changing slowly, you would think, well, we don't need to sample it quite as fast, and that's the intuition we're going to try and pin down precisely mathematically. All right, so I would write this sampled cosine. I would just use the formula, again, I'll write it over here. X of n equals x of nts. So I just take the sampled, the continuous time waveform, and wherever I see a t, I evaluate that at n times ts, where n is an integer. Okay, so doing that, I would get the following expression, right? Just plug in this n times ts for t, and that gets multiplied by 2 pi f naught. All right, and so ts, again, ts equals 1 over fs, where fs is the sampling period. So I can just write that as the ratio between the frequency of the sinusoid, f naught, and the sampling frequency, right? What's circled right there. We're actually going to define that to be the discrete time frequency. So the ratio, again, of the frequency of the sinusoid to the frequency of the sampling rate. Okay? Excuse me, that frequency of the sinusoid to the sampling frequency. That ratio is going to be defined as f hat, and that's again referred to as the discrete time frequency. That's all written right here. Okay, and we'll see exactly why we do this in maybe not this lecture, but the following lecture. And intuitively, when we're looking at this f hat, think of this as, again, it's the frequency of the sinusoid, which has units of hertz or cycles per second, and then that's over fs, where fs is the number of samples per second. It's sampling frequency. Okay, so the unit of f hat should just be cycles per sample. So what does that mean? F hat tells us the number, in between 2 points, the number of cycles of the sinusoid that we actually have. So we would think f hat should be, if we're sampling a lot, f hat should be small, right? We'd have a small number of cycles of the sinusoid in between 2 sampling points. And that's indeed the case. So let's see, again, another example. Now we'll just pick the cosine with the frequency 100. Okay? And that's drawn right here. And if we sample that at a sampling period of t naught equals 5 milliseconds, how does that look? Well, we take the first sample at time 0, right? And this is again just by using that formula. We say x of n is actually then equal to x of n times ts. The second thing I said was a continuous time waveform. So setting t naught equals 5 milliseconds gives us a discrete time frequency, right, f hat of, now we take the sampling frequency divided by, the frequency of the sinusoid divided by the sampling frequency. Okay, so the frequency of the sinusoid times the sampling period, and that just gives us 1/2. Okay, so we're taking a half, there's a half a cycle per sample. And we can see that just from, excuse me, the picture it's drawn on the top of the screen. And when we sample the signal, really we just get these values. This first one takes value +1, right? The second sample we get -1. Third one again is +1. So we go back and forth from -1, +1, -1, and so on. So let's think about what happens if we actually reduce the sampling frequency. So that means increasing the sampling period. If we set the sampling period to be, say, 10 milliseconds. Then you can see we don't take a sample at 5 milliseconds, right? And then we seem to just, we're missing a lot of the interesting things that are happening with the signal, right? Take the first sample at 0 milliseconds, second one at 10 milliseconds, and we can see that x of n, this discrete time signal, just ends up being 1 for all values of n, right? So there's a bit of a problem here, and if we calculate the discrete time frequency f hat, we see that there's 1 cycle per sample. Okay? And that's not enough samples to accurately be able to reconstruct the signal if we were just left with the signal x of n. Right? It's the same, we can see that it's the same as just a constant signal. So after sampling, we have x of n is drawn in this plot here. Right? The values are just constant value of 1 for any value of n. And that's a problem, right? Because this also could have represented a sinusoid with a frequency of 0, or just a constant signal. And so that's what's called aliasing. So aliasing in signal processing and electrical engineering is just referring to when we take a signal, we sample it, but we don't sample it fast enough. And that results in there being multiple different signals that could represent this same discrete time frequency. So multiple continuous time signals could give us the same discrete time signal. And so that's referred to as aliasing. And we'll spend the rest of this lecture and the next lecture talking about that. Okay. So what would be the solution so we don't get aliasing? Well, of course, if we just increase the sampling frequency, right? If we increase f sub s, which is the same as decreasing the sampling period, if we do that, then we can see just from this picture, we're now taking, with the same example, 1,000 samples per second, and we're, much better. Our ability to capture the variations in the sinusoidal signal are much better. And just as a note, and what we'll talk about next time is aliasing occurs anytime the discrete time frequency is greater than 1/2.